Hey guys, my name is Brandon Funke. I'm the product manager here at 3DX Tech, and today I've got Matt Howlett, our founder, with us.
Hello.
So today we're going to do something a little bit different. We're going to do a deep dive into the nylon family. So nylons are a pretty tricky material. It's a whole family with a lot of different products in it, and we get a lot of questions about how do you select the right nylon, what are some tips and tricks about nylon. So we wanted to bring Matt in and allow him to really do a deep dive into this product family and get you guys in the know and let you pick the right material for the upcoming applications.
Yeah, that's really it. Thank you, Brandon. So I've been selling nylons for probably 30 years in various companies. Started this business 10 years ago. But whether it's the more basic nylon 6, 6.6, nylon 4.6 I was selling for a period of time, moved into the PPAs, the high performance nylons, and then later into carbon fiber and other composites. But as Brandon said, nylons are a pretty tricky one. People will ask us, hey, what's up with this nylon, or how do you compare your nylon to this nylon? And there's so many of them that I think this would be pretty timely to take a look at this and get a little deeper into it. So with that, let's get into the presentation. All right, so let's get into it. So a little bit about 3DX Tech before we get started into the nylons. The company was established in 2014. We're in Grand Rapids, Michigan. We have 68,000 square feet under roof that's dedicated to manufacturing our products. I think it's safe to say that we have probably one of the widest, if not the widest, array of materials that we manufacture. Everything from carbon fiber, ESD, glass fiber, flame retardant, many high temperature materials like PEC and Altem, TPIs. And we also, depending on the customer needs, we can make custom materials. Some customers will come to us and have a very specific formulation in mind. They need a density or a certain type of electrical capability, and we'll have that material custom made. And then we can do toll compounding for them as well. So with respect to nylons, I think it's safe to say we've got a pretty broad array of nylons that we manufacture. So you'll see here, the PA6, 6.6, PA12, we've got carbon fiber 6, 12, and PPA, a high temp nylon, glass fiber 6, 12, and PPA. One of our better selling and actually a really interesting material that we developed is our ESD PA12. And we have a friction and wear grade that uses PA6 and molybdenum disulfide. And we have a couple customers that continually use, actually from the beginning of the business, our Ion Nylon 6 ABS alloy. Interesting too, I wanted to note that we created a couple grades of carbon fiber and glass-filled nylon that we're targeting, that are targeting specifically the Mark Forge customer group. So if you're using one of their printers, the Obsidian grades were designed to drop right into the Mark Forge machines using their preset settings. So a little bit about basic terminology. We get a lot of questions about nylon, and it as Brandon mentioned earlier, covers an incredibly wide array of materials. So nylon and polyamide, we get questions. Some people have a limited familiarity, so we figured we'd start from the beginning here. Polyamide is the same thing as nylon. The short for that is PA, which again is polyamide. PA is also therefore nylon, and PA6, for example, would also be nylon 6. So when you see the terms polyamide or nylon or PA or PA6 or PA12, those are all interchangeable. So we're talking about polyamides and nylons in the same terms. Polyamide, just where it comes from, and this digs a little bit deeper into the types of nylons and chemistries that we're going to get into for a couple slides. Poly is, of course, many, and amide is an amine and a carbonyl group, which the image off to your right kind of shows both of them, how they would be linked up. So broadly, there's three types of polyamides. There's the aliphatic, the semi-aromatic, and the aromatic polyamides. The aliphatic polyamides are the ones that most everybody in the 3D printing industry are more aware of. The PA6s, the PA11s, PA12s. PA46 is a pretty common polymer from DSM in other industries. We really don't see it in additive. But these are, and you'll see in slides in the next slide or two, that these are more linear. They offer a little bit more flexibility in the backbone, and they tend to have a little bit lower performance, both mechanically thermally and chemically than the other two. Semi-aromatic, these are nylons that have a fairly large ring structure in the backbone. This limits its flexibility, but adds a lot of temperature and chemical resistance. These are also known in the industry, some companies call them HTNs or PPAs. That would stand basically high temperature nylon or polyphthalamide. Examples that you may have seen, you may not have seen, but we sell some of these and some of our competitors do are PA6T, PA9T, PA6T6I, or PA6I6T. There's a bunch of different ones. And then the last one would be an aromatic polyamide, not really germane to this conversation, but these would be fully aromatic materials, which are actually materials like Kevlar and Nomex. As the traditional nylons go, they're not really what you'd expect to see in this family, but they're technically in the PA family, so I wanted to include them just in this part of the presentation. So when we get a call from customers and they say, hey, we'd like to, tell us a little bit about your nylon, or we have a nylon from supplier X, how does it compare to yours? You can kind of see from this slide that there is a broad array of nylons, and this isn't even an all-encompassing list. This is many of the more common materials that are used throughout the plastics industry, but definitely not an all-inclusive list. So the aliphatic materials, they're all semicrystalline. They range from materials like we sell PA666, PA6, PA12, but there's many of them in there. The semi-aromatics are where things start to get interesting. The chemistry allows for significantly better thermal properties, better chemical resistance, better mechanical properties. But as you'll see in the next slide, these are a little bit more complicated chemical structures. They tend to be a little bit more expensive, but you kind of get what you pay for. So you get the PA6T is pretty common, PA9T. These materials offer significantly better properties than the aliphatic semicrystallines. Now, semi-aromatic is it can be both amorphous and semicrystalline. The amorphous ones are the PA6I6T. What's interesting about these is that these are all both amorphous and transparent. So you can have some really good temperature, mechanical, and chemical resistance properties, but also have a part, especially in some processes, injection molding, blow molding, but also in 3D printing, where you have enough light transmittance through the material that you can have a pretty transparent part. And the last category I put in there because we sell a material, ion, but you can have nylon alloys. So these aren't blends. They use usually another polymer or another compatibilizer that will allow the PA6 or PA66 typically to alloy with these materials. You get a blend of properties of both, and really is an interesting way to enhance the base nylon. So into a little bit of chemistry, and not a deep dive because I don't want to do that to anybody and I don't want to do that to myself. But basically these are long chain polymers that are made by the condensation polymerization process. So essentially these monomers are reacted, and under pressure and temperature and water is released. And we're going to want to remember that water later because as anybody knows who's played with a little bit of nylon, moisture tends to be your biggest issue. And one of the reasons is the way that these materials are polymerized, nylon and water kind of start together and they want to get back together again. So essentially there's two different types of nylons in the way that they're polymerized. There's a ring opening polymerization, which is the first one here, and then there's a diamine and a diacid, which is the second types. So an aliphatic, and when you say aliphatic, kind of in your mind, think of a long chain, fairly linear, no big cyclical or ring structures. And again, these are materials like PA6, PA12, things that we're accustomed to hearing in this industry. These use single monomer aliphatic polymers. So if you see a PA6, it uses one monomer in the reaction. So it'll use, in PA6's instance, it'll use caprolactam. So technically that would be polycaprolactam. And PA12 is laurolactam, so polylaurolactam. So they're a little bit simpler polymers than, say, some of these dual monomer. We don't see as much of these dual monomer polymers in 3D printing. So materials like PA66 and PA610, they typically will use a those two numbers indicate that they use two monomers. So in this instance, it's HMD or hexamethylene diamine and adipic acid for PA66, or hexamethylene diamine and sebacic acid for PA610. And again, as I mentioned earlier, the semicrystalline, the PPAs, this is where it gets really interesting because you end up with aromatic diamines and aromatic diacids. And that little twist on the back end gives you a world of different opportunities with respect to chemical resistance, temperature resistance. So in this, so you can see the PA6T6I is somewhat similar to the 6,6. It uses HMD, but on the acid side, it uses two different acids, a terephthalic acid and an isophthalic acid. So you can see some of these, it's usually the terephthalic acids and the isophthalic acids that make the PPAs the higher temperature resistant of the PPA or of the nylon families. So here's a little bit about basic structure. So often, what's the difference in someone's mind about a PA6 or a PA12? And it's really the amide group, which we covered in the previous slide, but the amide group, how far apart are they on the polymer chain from each other? So you can see in these basic representations, the polymer chain would have 6 carbons in it, and it would be a PA6. So between functional repeating groups, how many carbons are on the backbone pretty much indicate what the chemistry is. A PA6, PA12, PA11. All the chemistries look relatively the same. You'll see it gets a little bit more complicated in the next slide when you get into the PPAs. But when people think about PA6, PA12, now you know why. So this ties into a couple different things. You can see that there would probably be more. You can imagine PA12 being a little bit more flexible than PA6. It's a longer chain. There's a longer distance in between the two functional groups. So you could imagine it being a little bit more pliable, a little bit more flexible. PA6, it's a little bit closer together. You probably have a little less bending. It's a little stiffer polymer. We'll talk a little bit about moisture properties here soon. But one of the things is the nylon group, or the amide group in here, absorbs more moisture. So the further these are apart in the repeating unit, there's fewer of them per mole or per kg of polymer. It's going to absorb less moisture and create fewer problems. And again, as I mentioned, this is where it gets kind of interesting because again, you'll see this is represented in a way that you get this large cyclical structure at the end, which in this case it would be a terephthalic acid on the right side of these polymers. The PA6T would use a C6 diamine, which, if you recall from the last slide, is a HMD or hexamethylene diamine. But the principle is the same, whether it's PA6T or PA9T, is that you've got between functional groups, you've got six atoms of carbon between them, or 9, and the moisture absorbing portion, which tends to be in these molecules, the NH group. They're further apart. There's less of them per kg, per mole of polymer. So PA9T would absorb less moisture than PA6T. PA4T, which is a new polymer in the last, call it 8 to 10 years in the industry, will absorb more moisture than any of these, because there's more repeating NH groups per mole of polymer. So kind of follows through that these materials will be higher performance, but also lower moisture absorption. All right, so let's talk a little bit about the advantages and disadvantages of nylons. So one of the overarching advantages of nylons is its broad array of thermal properties. So whether you're on the aliphatic side, the lower temperature, all the way up through the semi-aromatics, you can get a pretty broad range of thermal properties depending on what you're looking for in your application needs. Again, its thermal chemical properties can range all the way from relatively low on some of the aliphatics all the way up to quite high on some of the semi-aromatics. This material has a relatively low density compared to some of the light metal alloys that you can replace. It's inherently electrically insulative. Can be made non-halogen flame retardant. So there's a lot of companies out there that can sell additive packages that can make nylons non-hal, FR, all the way up to V0, very thin. Readily accepts reinforcements and additives, as we've mentioned before, but some of these other materials can't do that. This is one of the distinct advantages of the nylon family. The amorphous types of nylon are transparent. So depending on the needs of your application, if you happen to be able to see through, whether relatively transparent or fully transparent. Some of those nylons can get you that. They can be bio-based. So PA11, for example, is based off castor oil and is a renewable polymer. They have a general ease of processing. They range, especially on the low end aliphatics, melt temperatures of say 190, 195, all the way up into the semi-aromatics in the low 300 Cs. So there's a broad array of processing temperatures that these materials have. And they have a general good wear resistance, better than some of the other engineering polymers. Disadvantage. One of the key disadvantages of the entire nylon family is its moisture absorption characteristics. So as mentioned in some previous slides, the NH group absorbs or has an affinity to the H2O, and the fewer of them in your polymer chain, when you go to long chain aliphatics, say like nylon 11s and 12s, or into the semi-aromatics where there's fewer NH groups and they're protected by that large benzene ring structure, you end up with a lower moisture absorption. What happens when the material absorbs moisture? So you end up with a reduced stiffness. So let's just say tensile modulus, and we'll see in a following slide. Your tensile modulus might drop up to 50%, depending on the type of nylon it is and how much reinforcing filler it has in it. It absorbs moisture, so it's volumetrically it will swell. The moisture's got to go somewhere, so your dimensions will get larger. Many applications, it's not a huge deal, but if you have a really critical application and you absorb a lot of moisture, it can throw you out of tolerance. And then, of course, what we all see all the time, anytime you've printed wet nylon, you have processing difficulties. So there'll be steam, bubbling, surface defects, interlayer delamination, general poor mechanical strength. Then there's hydrolytic stability, which is a close cousin to this moisture absorption issue. But what this is when the material absorbs moisture and is under temperature and pressure, you can actually depolymerize or unzip the backbone. And you'll end up with degraded properties. You really can't come back from that when you dry it back out. These are, again, polycondensation polymers. Moisture is given off. If you put it in the environment of moisture and heat them back up under pressure, you're going to kind of put that moisture back in there. Another disadvantage, kind of like they're easily made non-halogen flame retardant, they're readily flammable without it. So if you have the potential for fire around your application, you probably don't want to use an unfilled nylon that isn't flame retardant package, because they are pretty readily flammable without the package. And then across the board, whether it's the aliphatics all the way up through the semi-aromatics, they generally have poor UV resistance. So if your application is going to be outside for any extended period of time, unsurface treated, painted, clear coated nylons probably aren't the right material. There may be better materials for you to choose. So here's a graph about the moisture absorption. So as you can see, the moisture absorption, and kind of alluded to it in other slides, the moisture absorption is directly related to the polymer structure. So if you have a smaller chain and there's more NH groups that have the affinity to the moisture, you can imagine you're going to end up with more moisture absorption. If you have a longer chain and fewer NH groups, or as you see in some of these terephthalics, they have that large benzene ring in the backbone to help protect from some of the moisture absorption, you'll end up with a little bit lower moisture absorption. And that will play itself out in mechanical properties and swell, what have you. But if you're going to be in a moist environment, then maybe say PA6 isn't the material for you if retention of mechanical properties long-term is what you're looking for. Here's another slide with respect to moisture absorption. So you can see the PPA in the green starts off at the highest flex mod, and it retains the most flex mod out of the materials. This specific PPA is a relatively long chain PPA, and it has the best hydrolytic stability and moisture absorption properties of any of these. The PA6, as you can imagine, from the earlier pages, we talked a little bit about that it has a smaller chain in the back, and there's therefore more NH groups that can be attracted with the moisture. So it may start off a little bit stiffer as a material, but once this material has been exposed to humidity long term, it actually ends up at lower mechanical properties than the PA12 does. And again, with the PA12, Starts off a little bit lower than 6, but actually ends up a little bit better properties than PA6 does after full immersion for 30 days. So move on to thermal properties. So thermal properties are all over the spectrum with this material. So when you talk about the aliphatics, things that, again, we're used to in this industry, PA6, PA11s, PA12s, they tend to be on the lower end of the thermal properties in this range. So we're used to seeing materials that are either unfilled or glass filled or carbon fiber reinforced, that if you were up into the 200 degrees C range of thermal properties, you're doing pretty good. Whereas with the semi-aromatic nylons, which we have a couple in our portfolio, they have melt temperatures around 300. So properly reinforced and formulated, you can get good mechanical properties up into the 260, 270, and even 280 range, depending on the formulation. Amorphous nylons are a little bit different. So in general, amorphous materials, whether they're nylon, ABS, anything else, your load-bearing capability under temperature and pressure usually is around 10 or 15 degrees below the TG of the material. So amorphous nylon, say a 6I6T has a TG of 125. Whether you put 10 or 20% glass fiber or carbon fiber into it, the most you're going to get out of HDT or the heat distortion temperature is probably going to be around 110 to 115 degrees C max. So these have their specific uses and purposes, but if ultimate temperature, something you're going to see at 240 degrees in your end use, amorphous polymers probably aren't going to be what you're going to be selecting. So let's talk a little bit about these mechanical properties. So as the temperature performance of each material is a little bit different based on whether it's an aliphatic PA6 all the way up to a semi-aromatic PA9T. These all change based on how you reinforce them. So an unreinforced nylon, whether it's an aliphatic or a semi-aromatic, is going to have a little bit lower properties across the board. But if you start to reinforce it with some carbon fiber or glass fiber, you get a pretty significant change in mechanical properties that you may not see in an amorphous material. So here's a good example. You put carbon fiber into the same material, you end up with a tripling of the mechanical property. This one's here specifically is tensile modulus. Glass fiber, it's a little bit less efficient at making things stiff, but it adds other things. You can put more glass into it. You end up with better dimensional stability, better strength, not necessarily stiffness, and a whole lot less moisture absorption because you're actually displacing a whole lot of nylon because you can more heavily load it. Same could be said with other reinforcements that change properties, whether it's, again, talc, mica, some of the wear additives that we put in, other companies might put in, like molybdenum. They do different things to make it stiff. So the mechanical properties of these materials can be greatly varied by what additive packages you put in. And chemical resistance. Again, we talked a little bit about chemical resistance earlier, that's one of the strong suits, but you got to pick and choose your battles. There may be better polymers depending on what chemical environment you're going to see. So again, nylons resist nonpolar solvents, including aromatic hydrocarbons and esters, essential oils. So things that are under the hood, gasoline, transmission fluid, engine oil, typically not a big problem. But they do get softened and become lower properties. You end up losing quite a bit of properties when they're in the presence of polar materials such as alcohols, glycols, and water. But again, this isn't a one-to-one comparison. So if you're in glycol, for example, there's quite a few applications where nylon 6,6 are used in lower temp glycol applications under hood. It might be fine. But if it's on the hot side of the engine and you have pressure, a PA66 isn't going to work. You're going to have to move up to something that's got better temperature and chemical properties, such as a PPA. So as a general rule, and again, there's instances for each one of these, but if you had to think, I'm worried about chemical properties for my part. In the order of hierarchy, PPAs in the nylon world are going to have the best chemical resistance properties, followed by PA12, and then PA6. Again, there's probably instances where you can find that one might leapfrog the other. But as a general rule, if chemical resistance is what one of your worries, this is where I would lean towards. So best practices. Everything, I think you probably heard on half a dozen slides now, something to do with moisture. Moisture is the Achilles heel of this product, of this whole family. So when we get questions, emails, complaints from customers, we always go back to moisture first. We take great care when we make the material. We extrude it, we keep it dry. After it's wound, we actually dry our nylon materials overnight and package them up while they're still warm with a bunch of desiccant in there. So our goal is to supply you dry material that's ready for you to process. But things can happen. The bags can get pierced. There might be a packaging issue, might have been a bubble in the seal. You may have opened it up, put it on your printer, it worked fine, but then the next day or two you go back to it and it's absorbed too much moisture. And it needs to be dried out. So moisture is probably, out of the top 10 problems, it's probably 1 through 7. It really is a significant part of the issues. So when you do find yourself with moist nylon, whether unfortunately it may get shipped to you that way from me or another supplier, or it's been out exposed in your shop for a period of time, material has to be dried out. The good news is it's relatively easy. You just have to have the ability to dry these materials, say PA6 and PA12, the more common materials. We recommend about 90 degrees C, 6+ hours. If it's been out in your shop for months and it's been humid, you might have to go overnight. It absorbs a lot of moisture. It takes a while to come off. If you're lucky enough to live in Chandler, Arizona in the summertime or the winter, let's say, and there's no humidity, you probably can dry it for 4 hours and it might be fine. PPAs, the high temperature nylons, take up less moisture, but they give it off a little bit more difficultly. So those materials need to be dried at 120 C for 6 hours or more, and you should get back into printing without problems. We make our reels, just as kind of a side note here, we make our reels out of materials that can withstand these temperatures. So we wouldn't put a PPA on a low temp reel, for example, that would fail at 80 C like an ABS reel. So all of our higher performance materials are put on reels that can withstand being dried up to 150 Celsius. The next tip, if you will, for being able to print nylons better, if you have a printer that has a enclosed chamber and you can heat it, you typically want to be in the 60 to 120 C, I'd say 90, but somewhere in that range for these aliphatic polymers. And PPAs, you want to be 120 to 140 C. If you don't have the ability to heat your chamber, then just enclosing it and having it be sympathetically or otherwise heated by the bed and maybe the head, anything's better than nothing. So if you can enclose your print chamber and maybe put a small heater in it or just let the bed heat it up, that's still going to be better than having it be out in the open and being exposed to just regular ambient air in your room. The other thing, we sell a lot of reinforced grades. So I put this in here because whether it's carbon fiber or glass fiber reinforced, we have a lot of customers that will get a hold of us and say, hey, your carbon fiber nylon is jamming the nozzle. And so we use a solid, good carbon fiber. Starts off as a chopped carbon fiber. We try to do everything we can, both through compounding and extrusion into filament, to try to retain the length of the carbon fiber so that translates into better properties. But still, they're pretty small, so they shouldn't jam your nozzle. What we've seen usually is customers will try to set up a nozzle and the layer height up, let's say 0.1 or 0.15 millimeters, because they want to try to get the most pristine surface. And what happens is, if you can imagine, the fibers orient themselves in the direction of flow. So as the polymer is flowing through your nozzle, the fibers line up with that. And as they exit the nozzle, they have to take a sharp left turn, essentially, as this material is being laid out. It has to turn. It doesn't really like to turn. It's a stiff fiber. So as you're doing that, you're going to build up head pressure. And as you build up more head pressure, you end up getting the drive wheels to bite into the filament, and you get a non-flow, non-feed situation. So typically, if you back off the layer height, we recommend 60% of your nozzle diameter is your minimum layer height. So if you do that, let's just say you're using the 0.4 nozzle, 0.25 would be your minimum layer height. You'd be surprised how pristine the parts can look. The fibers actually mat out the surface and give us a really nice surface. Usually that will get rid of a lot of your jamming. And then bed prep. So we got lift, you got warp. The lift is usually caused by the air and the bed adhesion. But if you use something like a Magigoo or a nanopolymer adhesive, we sell both. Have it a relatively heated bed, somewhere between, let's call it 60 and 100, depending on the material and the printer you're running. You should get really good layer bonding in those first couple layers and help alleviate most of your lift issues. So these are the big ones that we've seen over years of selling nylons. If we had to distill all the issues down, these 4 things can help solve most of your issues in printing nylons. So with that, I think we're going to open it up, Brandon. You ended up with some questions from some of the folks that you wanted us to take a shot at.
Awesome. Well, thanks, Matt. That's a lot of information. That was a lot of really good information that I think our customers will find really beneficial for them. Like you said, we get a lot of questions from customers on our nylon. So I've got a couple written down here that I thought would be really good ones to pass off to you and really just kind of pick your brain and see what you thought about it.
Sounds great. Let's do it.
Yeah. So the first one I've got, we do get this one a lot, which is which support material would you recommend for printing nylons?
So not every nylon's the same. So we have a material called X1, and it's a water-soluble, cellulosic based. Works pretty good. If you're going to use it in a high-temp heated chamber, say with our PPA at 130, 140 C heated chamber, you're probably going to want to use our nylon breakaway support. But for the most common, just general purpose printer out there, the X1, if you can tune in the inner layer between the support and the model material, you're going to get pretty good results.
Okay, perfect. So the next one actually revolves around, I got this one a couple days ago, and I thought it was kind of a timely question because I thought it would fit in really well. Customer came in asking, hey, so my application entails exposure to hydrocarbons and road salts, so it looks like we're dealing with a potentially under the hood automotive application.
Right.
How should I go about selecting the right nylon for this material, or for this application?
Yeah, that's a good question. So again, this kind of ties back into my automotive days. Not all nylons are right for every application. Mm-hmm. So for example, PA6, our 666, for example, PA666, in glass fiber, unreinforced, could be good in something. So the road salts, the zinc and calcium chloride, for example, makes me take pause on some of those lower end materials like a PA, like a PA6. It may be fine in the hydrocarbons. Wouldn't have an issue with underhood. I mean, if you imagine the intake manifold in pretty much every car out there is glass filled nylon 6. Mm-hmm. So it's going to get incidental splashing, if you will. There's probably going to be some road salts that get up to it, but not a high level of exposure. If you talk about clips or fuel lines or anything under the car, where you're going to get constant, especially in the winters in the north, you're going to get exposure to the road salts. PA12 might be a little bit better. Mm-hmm. PPAs, the high temperature nylons, will be significantly better. So there was, in my, again, a previous life, we had a lot of data that we're showing the OEMs that PA6, albeit a little less expensive and a little friendlier to their pocketbook, didn't really last that long in road salts. Whereas the semi-aromatic, the PPAs, lasted considerably longer, and you could count on them to withstand a lot of those road salts. For any of them, if it's just hydrocarbons, if it's motor oil, for example, they're all going to be fine. It's a pretty big molecule. It's not going to hurt the nylons. But it's the road salts on that one, which would lead me more into the long chain or into the PPAs.
Gotcha. Awesome. And so I saw on one of the previous slides you were talking about how nylons had a pretty wide variety of of temperature ranges.
Yeah.
So what temperature range, if we've got a lot of people that love nylons, a lot of people like nylons. So when they're finding applications, they try to say, okay, I like nylons, I know how to print nylons. Here's this application, which nylon do I select for that? So if you're going to see a temperature range, at what point do you say, okay, now I've passed the limit of a nylon?
So it can go both ways. I'm going to have an answer for you there that you wouldn't expect. There are temperatures, higher temps, that you don't want to go beyond. Mm-hmm. There's also lower temps that don't make sense to use nylons. So let's go on the high end. So if you take a look at, say, nylon 6, traditionally you can get up to, let's call it 200, 210 max, but let's just say properly reinforced, 30% glass fiber, nylon 6, you can get up to 190, 200 C. Mm-hmm. Everything below that should be fine, right? The PA12's a little bit lower. I think the melt temp just top of my head, somewhere around 175, 180. So properly reinforced, you're probably going to be in the 150s or something for that upper mechanical load.
Yeah.
PPAs, however, you're at 300 degrees, 320 on some of them. So let's just say 300 for, if you put proper amount of glass or carbon fiber reinforcement in there, you could probably get load bearing capabilities up beyond 260 to 290 degrees Celsius. So that's covered. So the flip side of it, which I kind of was going to toss you a little curveball, is there's temperatures in which I probably wouldn't even use nylon because it's not necessary.
Yeah.
So we covered it more than once, I'm sure. But its biggest Achilles heel is moisture. So you print something, at first it seems pretty stiff, you leave it on your desk for a week and it's kind of flexible. There's nothing wrong with the nylon, it just absorbs moisture. So if your application isn't going to see temperatures, say above 80 C, you're not going to see horribly aggressive chemical environment. I'd probably use carbon fiber PETG.
Okay.
You know, it's easier to print. It's probably a little less expensive. You don't have, with polyesters, you don't have the moisture absorption issues as much. So if it was an application, let's just say broadly 75 C and below, which is, I mean, let's be honest, a broad array of applications, I'd use a glass-filled, carbon fiber-filled PETG. It's going to be a little bit cheaper, a little bit easier to print. And again, the part was going to retain its mechanical properties long-term without the degradation of the mechanicals.
Gotcha. Yeah, so it really just comes down to...
It comes down to it. The good news is we have a pretty wide array of materials. We got a lot of tools in our toolbox. So we don't have to peg somebody in to something just because that's all we have.
Yeah. So the next two questions I've got are actually from me. The questions that I've been wondering about specifically are nylons for you. So if you looked at the product offering page that you showed in the beginning of the slideshow about the different nylons that we offer, we've got some of we've got a lot of the basic bases covered. We've got the nylon 6, nylon 12, carbon fiber, glass fiber, all of that ESD properties. But then all of a sudden at the end of the list, Werex pops in there. So that was one of the ones that was a little out of left field. It kind of broke the status quo with a lot of our nylon portfolio. What applications did you have in mind when you made that material?
No, that's a good question. So there's other ones in our portfolio, but that material was driven by customer demand. So a customer came to us and said, hey, we've got this nylon with molybdenum disulfide that we get stock bars in, and we machine them. And they were hoping to be able to find a filament that they could use that was also nylon with molybdenum disulfide in it for wear applications that they could print. That's something I made in a previous life in compounding, so I was able to make something for them, and it works really well. So again, the nylon itself is inherently has pretty good lubricity, but the molybdenum disulfide, again, allows for much more sliding and rotational forces before the material heats up too much, and then you start to gall and what have you. So that material specifically was meant for rotational, things like thrust washers. You have a constant force that's turning. So there's other wares that are more frictional that type of material wouldn't be the right material for, whether it was machined or 3D printed. But that one was really driven from a customer, and what we've seen is applications that somebody would want acetal. Acetal, every time I see that, whether it's in fuel systems, again, an old life, or things that are traditional friction wear in your house, the drawer slides. Those are made out of acetal. They have really good friction wear, real nice lubricious kind of surface. This material could be printed instead of that. Acetal, POM, extrudes nicely, prints horribly. So this could be a replacement in some applications that you would typically want to see acetal in.
Gotcha. Yeah, and one of the benefits of that compared to an acetal is you leave that in your nozzle and accidentally overheat it. You're not going to fumigate your house with formaldehyde gas.
Yeah. So with acetal, if you overheat it, formaldehyde's the problem. So what's the other question?
Yeah, so last one before we sign off, just kind of a little bit more of a fun question. So we've got a lot of nylons. Which one's your favorite? That's
a good question. So by and large, probably my favorite is the glass-filled, the 30% glass-filled 6. Comes in a couple different colors, whether it's flat dark earth or some of the, I've printed attachments for some firearms that are long lasting. They're really robust. But it's 30% glass fiber reinforced. We can offer it in a couple different colors. We have some brackets out on the extrusion lines that have been printed and are incredibly strong and durable after probably 8 years. So that material, again, it's 30% glass fiber. It's very strong, very stiff, very resistant to absorption of moisture because there's less nylon. So the more filler you can put in there, even though the PA6 in it's going to absorb some moisture, all that glass fiber and that matrix kind of holds things together. So we've got some parts here in the shop that if you made it out of carbon fiber reinforced nylon after a year, it'd be kind of bendable. That 30% glass fiber stuff has stayed stiff and strong for years.
Yeah.
So by and large, it's ease of printing. It's pretty affordable. It comes in colors. All told, it's probably my favorite glass, my favorite nylon.
Yeah, I think that's one of the big things. I mean, I'm like you, polymer engineer, so the mechanical properties, the chemical properties, and all of that, those always take chief priority. But then what you tend to see with a lot of the high performance materials is, I hope you like it in black. So being able to see
black,
it in different
prints
color
slower.
systems.
You go up into the PPAs, they can be a little bit more finicky. But if at the end of the day, you're going to use, whether it's PLA all the way up to the nylons, or even, you're going to use the lowest performance material, easiest to print, that your application requires. Yeah, it'd probably be great out of Ultim or Peak. Why?
Doesn't need to be.
Unless it has to be, don't use it. So, the least performance material that your machine can handle well is probably the right material for the application.
Yeah. Awesome. Again, thank you for that. I think that was really beneficial. I learned a lot, so I'm sure these guys did. So we'll have you back for a couple more of these in the future to go over some other material families. But until then, this has been Matt. My name's Brandon. Thanks. And if you have any questions, feel free to come out to the website at www.3dx.com for more information or reach out to our team. Thanks.
Take care.